Hello, my name is Kalyani Roham and today I am going to present my topic on time response analysis of first order system. This project has been completed under the guidance of Dr. Vijay Kumar sir along with my group members Vishal Sagar, Shubhangi Karare and Abhishek Dhamale. In this presentation, I will explain how the first order system responds to different types of input signal using a MATLAB simulink. A first order simulink is a system whose behavior is described by first order differential equation and it contains only one energy storage element such as capacitor or an inductor. The transfer function of the first order system is given by G of S is equals to K divided by tau S plus 1 where the K is the gain and the tau is the time constant. The time constant is the most important parameter because it determines how the fast system responds. Generally, the system reaches steady state in approximately 5 times the value of tau. In this project, we have analyzed the 4 standard input which are unit step impulse, ramp and last one is a parabolic input. Then starting with the unit step response, the unit step input represent a sudden change in the system. Like switching on a device, the output of the system for this input is given by y of t is equals to 1 minus rise to the power of minus t by tau. The system increase exponentially and gradually reaches its final steady state value and time equal to tau. The output reaches about 63.2% of its final value. The system shows an overshoot and settles smoothly within about a 5 times tau. This indicates that the system is stable and provides a smooth response. Now, the next is the impulse response to the input is applied for very short duration at the time t equals to 0 with very high magnitude. The output is given by y of t is equals to e. E means rise to the power of minus t by tau. In this case, the response starts from a maximum value and then decays exponentially to 0. This response represents the natural behavior of the system. Also, an important relationship is that the impulse response is the derivative of the step response. Then the next slide is moving on the ramp response. The ramp input increase linearly with time, meaning R of t equals to t. Means the output is given by y of t is equals to t minus tau plus tau multiplied by a rise to the power of minus t by tau. Initially, the response increases exponentially and after some time it follows a straight line. However, the system cannot track the input perfectly and there is a constant steady state error equal to the tau. This means the output always lags behind the input by fixed amount. Then finally in the parabolic response, the input is an accelerating signal given by p of t equals t square divided by 2. The output also grows in parabolic manner, but the system is unstable to follow the input accurately. In this case, the steady state error keeps increase with time, which means the system cannot track accelerating inputs. Therefore, a first order system is not suitable for such types of input. Now in the last is conclusion. In the conclusion, we see that the time constant tau is the most important factor in determining the response of the first order system. For a unit step input, the system gives a smooth response with a 0 steady state error. For an impulse input, the output decays exponentially to 0. For a ramp input, there is a constant steady state error equal to the tau, and for parabolic input, the error increases continuously. Hence, we can say first order system perform well for the simple input but is ineffective for the higher order inputs. And in the last there are the references. The references are control system engineering, modern control engineering, automatic control system, MATLAB and Simulink documentation and control system, and the very last is the lectures.
So my topic of discussion is the time response analysis of the first order system for the step, ramp, impulse and the parabolic input. First is the step response of the first order system, in which the state blocks is taken from the library. Next is the transfer function and the scope for the analyzing the response of the output with respect to input. So this is the first for the step response of the first order system. When we running this simulation, then we are getting the different values of the scope. So this is the green light indicating the step function and the blue line indicate the step response for the first order system, which is increasing continuously. Next is the impulse response of the first order system. Impulse response of the first order system, we all know that the impulse is nothing but the derivative of the step function. So that's why here one step function and there is one derivative of that step function and transfer function. When we open the scope of the impulse response, so here is a green light indicating one impulse, and this is the response which is exponentially decay or exponentially decreasing order. It is the response of that first order system when the input is the impulse. Next, we are going on the ramp response of the first order system. Ramp response is there is a directly ramp block is available in the library. When this ramp block is connected to the transfer function with a scope, then you know that the ramp is nothing but a one type of signal whose slope is 1 and which is increasing linearly. So when we opening that scope of the ramp, then you get that there is a linearly increment in the ramp function, and this is the response of that ramp function for the first order system. These are at a particular point this graph is increasing exponentially, but after some point it shows like a linear. Likewise it is showing in the this representation. Next is the parabolic response of the first order system. We all know that there is no actually parabolic function is available in this system, but when we give this signal to the integrator is nothing but when we take the integration of the ramp function, then we get the parabolic function, and when this input is connected to the transfer function via scope, then we are getting the output as the scope 3 is mentioned for the parabolic. So it is a parabolic function which is increasing exponentially, and this is the blue line indicating the response of that line, which is exponentially increasing, but that exponential is greater than the input. So it is likewise all the response of this all the systems that I see. So these all are the discussed how the step ramp impulse parabolic inputs give response to us for the first order system. So this is all about that.
Good morning, sir. My name is Abhishek Dhamale. Today I am presenting the first order system program. First, it clears the all data so that it result uh, are not affected by the old values. Then it defines the two important constant uh, and parameters. First is gain, which is k is equal to 1, and second is constant, which is t is equal to 2. The gain tell how much the output system will finally reach, and while the time constant tell us how the fast the system respond. After that, the system is written in the standard form of first order transfer function. uh, GS is equal to K upon TS plus 1. The equation represent how much the output how much output and input are related in the system. Then the mathematical model then this mathematical model is converted into a form that the MATLAB can understand, so that it can be used for analysis and plotting. Finally, the time ranges from 0 to 10 second is selected with the very small intervals. This helps in observing the system behavior smoothly over time. Let's see the step response. In this program, the step input means the input suddenly changes from 0 to 1 at t is equal to 0. The first response system cannot change output instantly due to the time constant. The output increases gradually with time. The response follows the exponential rise. Finally, the output reaches a constant value, means the steady state. There is no overshoot or oscillations. The system is stable. Uh, uh, this is the graph of the step response of the first order system. In this we can see the graph start from 0 at t is equal to 0. The output increases smoothly. The initial fast rise, then slow downs, gradually reaches the final value and becomes constant after the some time. Uh, no oscillation is equal to the steady response. Let's see the second RAM input response. Uh, in this program, the RAM input means the input increases linearly with the time. R of t is equal to t. The first order system cannot respond initial due to its time constant. So the output starts slowly and then increases. So the system tries to follow the input, but they cannot match exactly. The constant reference occurs between the output and input called the steady state error. The response is smooth and stable. There is no oscillation. Let's see the graph of the input ramp input response. The graph starts from 0 and increases continuously. Initially, the curve is slightly bent. After some time, it becomes almost the straight line, and system follows the input. The output line is always below the input, showing the lag. The gap between the input and output remains constant, a steady state error. No oscillations or disturbance in the system is tells the system is stable. Thank you.
Good morning, sir. My name is Shubhangi Karai. Today I am presenting impulse response. Impulse input is a very short and sudden input applied at t is equal to 0. It's represent a quick disturbance or shock to the system. In the first order system, the input does not stay high. It decreases with time. The response follows an exponential delay. The system gradually returned to zero, showing the stability. The speed of decay depends on the time constant t. It is a result of this impulse response. The graph starts from the maximum value at t is equal to 0. Immediately after the output start decreasing, the curve smoothly goes down. Number of oscillation. The output approach zero as time increase. This shows exponential decay behavior. No overshoot or oscillation. The system is stable. Uh, Parabolic input means input increases R is equal to R square by 2. The input grows faster than ramp accelerating input. The first order system cannot flow such fast changing input. The output increasing but much slower than the input. The difference between input and output keeps increasing with time. This means steady state error is very large, means infinite. The system is still stable because there are no oscillations. The graph start from the zero, the output increase in the curve. Initially slow, then increase faster. The curve becomes steeper with time. Output is always much lower than the input. It is the large error. No oscillation system is stable.